Alright, let's get started with what we're going to do today. As a reminder before I start, we're not going to have class on Wednesday. There still will be a video posted probably that morning or the day before, maybe tomorrow, whenever I get a chance to do it. So there's no class on Wednesday of this week, which is April 11th. Alright, so we get an extra hour and a half of your life back that day. And related to that, there's going to be no office hours the week after tomorrow. So no office hours Wednesday through Friday. Because I won't be here, that's why we're not having class. Alright? So that's the most immediate concern for this week. And then next week we have a few things going on as well for, as I mentioned in an email that I sent, we have course evaluations and an exam review next week. We'll give more information about that later. Alright, so today what we're going to do is we're going to finish Chapter 8, which is the chapter on gases that we've been working through. And even though our textbook, the title of the textbook claims to be an Adams first approach, in this chapter we're actually going to do an Adams last approach. Because today we're going to finally talk about the atomic molecular structure of gases and how those properties at that microscopic level correlate then with all of the macroscopic properties we've been talking about up until now, namely pressure and volume and temperature and all that stuff, and how those things are related. So what we're going to talk about today is called the kinetic molecular theory. And you know, the name, as the name suggests, it's a theory, which means it's an explanation for why gases behave the way they do, and it goes down to the atomic level to really get after that. So this is, of course, one of the great things about chemistry is the ability to use properties and things that happen at the microscopic level and correlate those to things that happen on a larger scale. And that's exactly what we're doing here. We're talking about those observable parameters for gases that we've been dealing with, and how does then the behavior of the atoms and molecules influence those. So there are 4 postulates of the kinetic molecular theory, or at least the way I've broken it down, it has 4. And so the first is we recognize that gases are made up of atoms or molecules, which I'll just generically refer to as particles. And what we assume in the kinetic molecular theory is that the particle volume is 0. In other words, the gas molecules have no volume themselves. Now we of course know this isn't rigorously true, but in a limiting case it would be, and this is, again, we're talking about gases that behave or that follow the ideal gas law. So what this says is that gas particles are essentially point masses. So they still have mass. We're not going to assume that the gas molecules and atoms have no mass associated with them, but they have no size. They have no volume. All right, and even though this, as I said, is not 100% true, when we're talking about a sample of a gas, we know that the gases are moving around, and it turns out that the volume of the empty space in that container is going to be much, much larger than the actual volume of the gas atoms and molecules. So to a good approximation, this would be true, and for any gas that follows the ideal gas law, this would have to be the case. So we assume that particle volume is 0, in other words, that all of the volume in a sample of gas is empty space, but there's still mass associated with each of the atoms and molecules. Now the one that's probably the most important is the second one here, at least that we're going to relate, how we relate this to the ideal gas equations, which is that these gas particles, these atoms and molecules, are in constant random motion. So they're constantly moving around all over the place. They're bouncing off each other, they're bouncing off the walls. And in particular, when the gas molecules collide with the wall of the container, that's what results in the pressure that we're able to observe and measure. Alright, so these gas molecules are zipping around in all directions, and at some frequency they're going to hit the wall of the container that they're in, and that's going to then exert a pressure. The third one is that the gas particles exert no forces on each other. So they do exert a force on the wall of the container when they collide. That's why we do see pressure being observed. However, the gas molecules don't exert any forces on each other. So there are neither attractive nor repulsive forces that exist between the individual atoms or molecules that make up that sample of gas. They're just buzzing around, they're randomly colliding with each other, but they're not influencing each other in any way. You can almost think of it as, if you were to take a jar of marbles and just shake it up really fast, the things would all bounce off each other, but they're not actually influencing each other, not attracting each other or repelling each other in any way. And then finally, what's going to be also important for things we talk about a little bit later today is that what governs how fast these molecules are moving, or what kinetic energy they have specifically. And so the average kinetic energy of the particles is proportional to the temperature. So the higher the temperature, they have more kinetic energy, and those two are directly related. And we're still talking about absolute temperature here. So in the limit of 0 Kelvin, which is absolute zero, they would have no kinetic energy. And then as you increase the temperature, the average kinetic energy of all the gas molecules then results in, the higher temperature results in higher average kinetic energy. And what this then has a result on some of the things we talked about previously is that the higher the temperature, the gas molecules are moving faster, and that means they're going to have more frequent collisions with the walls of the container. And each individual collision on average is going to have a larger force associated with it. Alright, so I think that kind of makes sense. If these gas molecules are flying around and hitting the walls of the container, which is causing pressure, if you raise the temperature and they start moving around faster, they're going to hit the walls of the container more often, and they're going to hit the walls of the container with more force. And both of those things are true when you increase the temperature, and that's going to then relate to some of the effects of temperature on the properties of a gas. So these are the 4 postulates, and even though we say them in much more precise language than this, the basic idea is that in a sample of a gas, the atoms and molecules are just buzzing around, bumping into each other, bumping into the walls of the container, and that's really what gives rise to all these properties that are associated with gases. And we're going to talk about some of these in a little bit more detail as we go through today. So the first thing let's go through is try to, again, relate microscopic to macroscopic level, and let's talk about then how what we just formulated with the kinetic molecular theory relates to the gas laws that we introduced this chapter with. So we learned a bunch of different relationships between pressure, volume, and temperature, and number of moles as well. And so let's think about then the relationship between pressure and volume, which we saw was called Boyles Law. And we know from the ideal gas equation that pressure is equal to nRT times 1 over the volume. This is another way of stating Boyles Law, which is that the pressure and the volume are inversely related to each other. When the pressure goes up, the volume goes down. And so let's see what happens if we change the volume of a container. So I'm showing here on the left is a container of gas with a movable lid or a movable piston, and we compress that down to make the volume smaller. We put, as they're showing here, just put a greater force on that to cause it to go down a little bit. So what we're doing here is we're decreasing the volume, and based on the kinetic molecular theory of gases, if we decrease the volume but we keep the temperature constant, the gas molecules are not going to move any faster or slower than they were before, but by decreasing the volume, they're not going to collide with the walls of the container more often. If you have a smaller container and they're moving with the same speed, they're going to hit the walls more often than they would in a much larger space. So if the volume goes down, the collisions become more frequent with the containers, the wall containers, so they're not more forceful. The molecules aren't moving any faster now, but the collisions become more frequent, and that's what's responsible then for the pressure going up. Alright, so we know that from Boyle's law that if you decrease the volume, the pressure increases, and at a molecular level, this is the reason why. The molecules aren't moving any faster, but they're hitting the walls more often, and that's going to then result in a higher pressure. So there's really 2 things that affect the pressure that's observed in a sample of gas. It's how frequent the gas molecules collide with the walls, and it's also then how forceful those collisions are, how fast the molecules are moving when they collide. So those two things affect it. In this case, when we just decrease the volume, we're only influencing the frequency of the collisions, but that would lead to an increase in pressure. All right, now let's look at the influence of pressure and temperature, or the relationship between them. So again, starting with the ideal gas equation, this was referred to as Charles's law, and what we saw was that pressure is directly related to temperature, so we can group all the things that are constant together and just look at the relationship between pressure and temperature, which we learned early on are directly related. And again, this follows then from the idea of when we increase the temperature of the gas, they're going to start moving around faster. So when we increase the temperature, the particles of gas move faster. That was one of the postulates that, and we know that we should recognize that kinetic energy and speed or velocity are related. So if you increase the temperature, you increase the kinetic energy, which then also increases the velocity. All three of those are related. We'll see the mathematical relationships later. So the particles move faster when you increase the temperature, and that means there's really two effects now. The collisions with the wall of the container become more frequent, and they become more forceful. So both of those contribute to the fact that the pressure is going to go up. All right, so if they're moving faster, they're going to hit the walls of the container more often, and they're going to hit the walls of the container with more force behind them. And so both of those are then going to contribute to an increase in pressure when we increase the temperature of a sample of gas, keeping the volume constant. All right, so those are the first two, which I think make a little bit of hopefully intuitive sense to us. And then we're going to talk about just a couple other relationships now that are along the same lines. Sorry, this was not Charles's law. I messed that up. Charles's law is volume and temperature, but it follows from the same thing we talked about just now. So again, the volume and temperature are also directly related. And it's really the same story that we saw last time. We're increasing the temperature of a sample of gas. The collisions are more frequent and forceful. So it's really that same concept. And if we're maintaining the pressure the same, which as shown here means we're keeping the same force or the same mass pushing down on the sample of gas, that's how they're depicting it in these illustrations. If we want to keep the pressure the same, the volume has to go up to keep the pressure constant. Or in other words, if we have the same weight pushing down on the gas, but now the gas molecules are moving faster, they're going to push up with a stronger force, and they're going to cause this to expand until the two forces are equalized, until there's no more motion. So it's the same concept as the last one, it's just this is talking about the relationship between volume and temperature when the pressure is held constant. And again, when you cause the gas molecules to move faster, they're going to collide with the walls of the container more often and more forcefully, and that's going to then result in this expansion that we see here. All right, and then finally, if we talk about the relationship between volume and moles, which is Avogadro's law, again, this is a pretty intuitive relationship that they're directly related. If we put more gas into a sample, it's going to have a larger volume. And this also then follows from the kinetic molecular theory. So what we're showing here is that if we have a volume of gas and we add more to it, the number of moles of gas increases. And if we're keeping the temperature constant, we're going to have more atoms or molecules of gas present. They're not going to be moving any faster than they were before because it's the same temperature. Temperature is the only thing that influences how fast they're moving. But if we cram more gas into the same space, if we have a smaller separation between them, there's going to be more collisions. Okay, so you're putting more gas into the same volume. There's going to be more collisions, and then of course that's going to cause the pressure to go up if the volume is held constant. If the volume is allowed to expand, that will also then increase to keep the pressure constant. Same story as the last one. Alright, so if we put more gas into this container while maintaining the same opposing force on the top of the container, if we put more gas in there, they're going to collide with this wall more frequently, and they're going to push it up, exert a force on it until the two are equalized. So these, there's really only one major driving concept here, which is that the pressure that a gas exerts depends on the frequency of the collisions with the wall and the forcefulness of those collisions. And there's different ways we can affect those by, altering the temperature or the volume or the number of moles. We just have to sort of try to think about these things on a microscopic level. So, any questions about those concepts before I move on? All right. So the next thing we're going to talk about, we mentioned that that increasing the temperature of a gas is going to increase the kinetic energy, and that's of course related to the velocity. So now we're going to talk a little bit more about the relationships between those in a little more quantitative detail. So first we're still going to approach it a little bit qualitatively and just look at some plots. And so what we have here is the idea of the molecular speeds. And even though the temperature will influence the average molecular speed, in any sample of gas, you're not going to have all of the molecules moving at the exact same speed. There's always going to be a distribution. Some are going to be slower, some are going to be faster, and they're going to have some average speed that's associated with them, and it's that average speed that's related to temperature. Okay? So that's the key thing to keep in mind when we're talking about gases, is that you don't have all of them identically moving in the same velocity or same speed, but in a sample of gas, there will always be a distribution of molecular speeds. Okay, so what does this look like if we plot it out? So what I'm going to show here are a couple of just crudely drawn graphs that show the fraction of molecules that are moving at a certain speed. So if we just take a sample of gas, as I said, they're not all going to have the same speed. They're going to have a distribution. So you're going to have something that looks like this. And again, it shouldn't actually go to zero. It should sort of asymptote to the axis. We can try to draw that more carefully. All right, so there's a distribution of molecular speeds that are present, and this peak here, which has the highest fraction of molecules, would be what you would call the most probable velocity. That's the one that more gas molecules have that speed than any other. But as I said, there's a distribution. There's going to be a bunch that are lower than that, a bunch that are faster than that, and then there's some average that's associated with this distribution. All right, so the one I'm drawing in blue here, I'm going to call low temperature. Now let's say we increase the temperature a little bit of this sample of gas, and we're going to draw this with a different color. All right, so we're going to increase the temperature of this, and as we said, when we increase the temperature, the average speed goes up. It's still going to be a distribution. So what we look when we go to higher temperature, we're going to have a broader distribution, and the peak is going to be shifted to the right towards higher velocity or higher speed. Okay, so this is what I'm going to call medium temperature. We're going to show low, medium, and high. So again, being pretty qualitative here. But the key concept is that the most probable velocity shifts to higher speeds, to higher values, because as we increase the temperature, the average speed of those will get higher. And then finally, the last one I'll show is what I'll call high temperature. So if we go to even higher temperature, it's going to broaden and shift even more. We still have a distribution, and then the peak is going to shift further out to higher speeds. Okay? So this is what these plots look like as we increase the temperature in a sample of a gas. So we're talking about the same gas in these. If we increase the temperature, the speed distribution broadens out a little bit, and the most probable speed, where this peak occurs, is going to shift to higher and higher values, which then correlates with the average speed of those being higher and higher. And so there's a relationship then between temperature and average kinetic energy, which is that the temperature is proportional to the average kinetic energy. And in this notation, we're going to put a little bar above something to indicate that it's an average. And as we know, the average kinetic energy would be given by 1/2 mv squared. This is from physics. So the average of the squares of the speeds times 1/2 times the mass times that gives you the average kinetic energy. So all these are related to temperature, and that's why as we increase the temperature, the average speed, which is approximately the point at the top of this diagram, of each of these diagrams, is going to shift to higher and higher values. So that's what happens when we shift the temperature or change the temperature in a single sample of gas. Now let's look at when we have different gases all at the same temperature. All right, so we know that if we have gases at the same temperature, they're going to have the same average kinetic velocity, kinetic energy. That's what we see here, this relationship. So what I'm showing here are going to be three different gases where they have the same average kinetic energy, but they all have different masses, so they're going to have different average speeds, okay? So if we look at, let's do O2 first, or again, this is all qualitative, but if we had a sample of O2 that had, let's say, some distribution that looks like this. All right, so that's what we're going to see for O2, for example. Now let's suppose we instead are going to compare this to a sample of helium. All right, so is helium lighter or heavier than oxygen? Lighter. Remember, O2 has a molecular mass of about 32. Helium has a molecular mass of 4, atomic mass, as it turns out. And so what we see here from this equation is that if they're at the same temperature, they have the same average kinetic energy, but helium is going to have a smaller mass. So if it has a smaller mass, it has to have a higher average velocity to account for that. So when you look at the distribution for helium, it's going to look something like this, where again it's going to be shifted towards higher values because the lighter molecules have to be moving at a faster speed to have the same average kinetic energy. Okay? So if we have the two different gases at the same temperature, they have the same average kinetic energy, but they can have different distributions of their speed if their masses are different, which is the case for these two. And then finally, if we go to even lighter gas like hydrogen, it would shift out even further by the same argument. All right. So what we can summarize this graph as is, if you had a given temperature, so all gases at the same temperature here, lighter gases will have a higher average molecular speed. All right, and that's something that's helpful to remember conceptually when we're comparing samples of two different gases that are at the same temperature. Their speeds will be different if the masses are different. All right, that kind of shows us then a graphical representation of all of this. And now we're going to get into some equations that are associated with this. Now I'm going to derive an equation here for the average speed, but we're not really going to use this in this exact form. But I'm going to do sort of a long derivation. It makes me feel a little bit like a mathematician to do this, although that's far from the truth. And so let's talk about then how we can derive an equation for the average molecular speed as a function of temperature. All right, we said that those two are dependent on each other. Now let's see exactly how they depend on each other. So the first thing is going to be sort of a given equation. I'm not going to derive this one because it comes from something called statistical mechanics, which is extremely complicated and not something I want to subject you to or myself to for that matter. So the average kinetic energy is going to be equal to 3/2 times the universal gas constant R, our familiar value of R, although we're going to use the one that's in units of joules instead of liter atmospheres, but it's the same constant, just different units, divided by Avogadro's number times the temperature. So that's the relationship between kinetic energy, average kinetic energy and temperature. As I said, those two are dependent on each other. And they're just related by a series of constants, 3/2 times R over Avogadro's number. All those are constants out in front of that temperature. All right, so just to define things clearly, R is the gas constant. This N sub A is what I'm abbreviating as Avogadro's number. And of course, T is the absolute temperature. All right, so there's a pretty simple equation then that relates average kinetic energy to the temperature, although we're not typically going to use this in the form that I gave it to you, but we should at least be familiar with that relationship conceptually. Now we can also rewrite this then as we saw on the last slide, the average kinetic energy is equal to 1/2 times the mass times the average of the square of the velocity or the square of the speed, however you want to think about it. We'll use speed and velocity interchangeably in this class because this isn't a physics class. All right, so we have this equation as well. That's the basic definition of kinetic energy, which if you've taken physics, you've likely learned by now. And so then we can just set these two equal to each other. 1/2 times the mass times the average square velocity is equal to 3/2 times R over Avogadro's number times the temperature. This is basically the average kinetic energy of a single molecule. We're putting in some more terms here. M is the mass of a single particle. And then this V squared with a bar over it is the average of the squares of the molecular speeds. Alright, so what we're concerned with here is the average speed. There's always going to be a distribution of speeds that would be described by the relationships we saw in the last slide. What we're looking at here is the average speed, and then we can set these two equal to each other. We can move things over, and we get 1/2 times Avogadro's number times the mass times the average speed squared is equal to 3/2 RT. And what we know from this course is that if we take Avogadro's number and multiply it by the mass of an individual atom or molecule, that is equivalent to the molar mass. So then making that substitution, putting in molar mass and then solving for the average speed, what we get is that the average speed squared is equal to 3RT over Avogadro's number times the mass, which is equal to 3RT over the molar mass. Alright, because again, little m is the mass of a single molecule. If we have Avogadro's number times that, that's going to give us the mass of an entire mole of that substance, which is the molar mass. So we write this equation, and then we solve for what's called the root mean squared velocity, which is just taking the square root of this. Again, it basically means average. It's a little bit different statistically. If you've taken the stats course, you'll know these details, but they're not important for us. And so the root mean squared velocity is just the square root of that, which is 3RT divided by the molar mass. Alright, and so that's the equation we wanted to get to, was an equation for the molecular speed, or the average molecular speed, in terms of the temperature, and everything else is just, we have a constant up top, 3 times R, and then in the denominator we have molar mass, which is characteristic of whatever substance we're talking about. Alright, so we see that the root mean squared velocity, the average velocity, depends on the temperature and it depends on the molar mass of the substance. Those two things are all that determine it. So that's the equation, and we can actually use that to calculate RMS, or average speeds, for different gases. So let's just do an example to give an idea of, how do we use this equation a little bit, and what are the numbers that come out of it. I don't think, don't quote me on this 100% because I haven't looked that far ahead into homework and test questions on this chapter yet, but I don't think we're going to actually use this equation exactly as it's given. There's another form of the equation we're going to derive that's a little bit more useful for us in this course. But let's just see how it works so we can get an idea for what these average molecular speeds look like. So let's say we have a sample of argon gas and the temperature is 17 degrees Celsius, and we want to know what's the average speed for those argon atoms at that temperature. Alright, so again, it's this equation that we just sort of derived. The square root of 3RT divided by molar mass. And when we're using this equation in this exact form, we do have to be a little bit careful with units as always. And so it turns out for this equation, since we're talking about speeds and we're talking about the relationship between kinetic energy and speed and all that stuff, that's where it all came from, the value of R we want to use is the other one, 8.314. Now again, this is not going to become a source of confusion for us, at least in this chapter, because we're not really going to use this equation exactly as I've written it here, but we're just for illustrative purposes, we're doing that here. And so we're going to have 3, and then we're going to use that value of R, which is 8.314 joules per mole Kelvin, because again, we're talking about the relationship between kinetic energy and velocity is where this came from. Kinetic energy would be in joules, not in liter atmospheres conventionally. Now we just have to multiply it by the absolute temperature, 17 degrees Celsius plus 273 is 290 Kelvin, so we have to use that temperature, always still Kelvin. 3RT, and then we divide it by the molar mass. Now the other thing that we have to be careful about here is because we're looking at, we're dividing joules by mass to get a velocity. Joule is related to mass, it's kilogram meters per second, so we have to do molecular weight in kilograms per mole. So from the periodic table, argon has an atomic mass of 39.95. We have to convert that into kilograms per mole to use this equation. And again, that's another source of confusion that would come up if we were to use this, but we're not going to really deal with it in the problems we'll see in the homework in tests. But if we're going to use this equation, we do have to be careful. We want it to be in kilograms per mole, so that the units actually work out. Because again, joule is the SI unit for energy, and that comes from kilograms, not from grams. Okay, so we put that in the denominator. And then what this comes out to numerically is 426 meters per second, which is fast, as you might recognize. So I think 1 meter per second, I think, is about 2 miles per hour, or maybe I have that backwards. But anyway, it's on the order of a few hundred miles per hour, or maybe as much as 800 miles per hour. It's really fast, okay? Faster than you'd ever drive your car, I hope, probably, or as are capable of driving your car even. And so this shows us that even at a relatively low temperature of 17 degrees Celsius, and even with a pretty heavy gas molecule or gas particle like argon, they're still moving around really fast on average. Okay, so it's a very, very fast velocity of these gas molecules, even at ambient temperatures like 17 Celsius, which is coincidentally about the same temperature as it is outside today. So they're moving around really fast even at these temperatures. And so that's hopefully what this will illustrate, even though, as I said, we're not going to really do these types of calculations on homework assignments. Now, the types of calculations we are going to do are going to be using a different form of this equation. And before I introduce that, I think I duplicated that slide by accident. Before I introduce that, we're going to talk about what's called Graham's law of effusion and diffusion, which is just another form of this same equation here. And so let's talk about what those two properties refer to before we talk about the equation that we're going to use to do this. All right, so it's called Graham's law, and it applies to both of these processes, effusion and diffusion. And so effusion is the escape of a gas through a tiny hole. Or what you might refer to as a leak rate. All right, so if we have a container of a gas and we puncture the container with a small hole, we know that the gas is going to leak out of there at some rate, and the effusion rate is how fast that process happens. So effusion is the leaking of a gas through a small opening, and then diffusion is the movement of a gas through another gas, basically, or the transport of a gas is maybe another way to think about this. Alright, so we should be a little bit familiar with the definitions, although the distinction between these is not terribly important because the mathematics and the equations that we're going to use are the identical for both. But think about it as effusion would be if I were able to take a balloon and poke a small hole in it without popping it, which requires some skill, obviously. But if I were to do that, effusion would be how long would it take. Effusion is the process of the gas leaking out of there, and the rate of effusion would relate to how long it takes for that balloon to deflate. Diffusion would be if I did that process up here and the gas starts leaking out of the balloon, how long would it take to go to the back of the room? So as we said, when you have a sample of a gas in any closed container, it's going to fill that container, but it's not instantaneous. If I were to take natural gas up here at the front of the room, which is laced with a little bit of a sulfur-containing compound to make it smell bad so that you can actually detect it easily. If I were to release some of that at the front of the room, eventually the people on the way back would smell it, but it wouldn't be right away. So there's always some diffusion rate, which is the time, which we relate to the time that it takes for the gas molecules to transfer over that whatever distance we're talking about. Okay, so that's diffusion, effusion. They're kind of two related but different concepts, but they both relate to how fast the gas is moving. So both of these rates, the rate of effusion and the rates of diffusion, are proportional to that VRMS, that average speed that we talked about. And I think this makes sense, especially for diffusion. If the gas is moving faster, it's going to diffuse faster through the room or whatever area it's diffusing through. And then effusion, if the gas is moving faster, it's going to more quickly find that little hole and it's going to escape. So both of these are proportional to VRMS. And what that means then, if we're comparing two gases, which is how we're going to typically approach these problems, if we have two gases, A and B, and we want to compare their rates of either effusion or diffusion, calculating the absolute rates would be difficult because there's a lot of factors that go into that. But if we're just talking about the relative rates of those two processes, we can just divide the two root mean square velocities for the two gases. All right, so even though the VRMS doesn't directly give us rates of effusion or diffusion, if we're talking about relative rates of effusion or diffusion, the ratio of those is going to give that. And then we just take those two expressions and we divide them. So for each gas, we saw that the VRMS was 3 times RT divided by the molar mass. So we'll do that for gas A, and then the denominator will have the same expression for gas B. And the only difference between these is the molar masses of the two gases. So we're going to compare effusion rates and diffusion rates at the same temperature, because that also affects things. And so if we have a constant temperature that for the two that we're comparing, this simplifies to give us an inverse square of the ratio of molar masses. All right, so we can just mathematically simplify this. 3RT divides out, and then we invert the fraction to get molar mass of B over molar mass of A, all under the square root sign. And so this equation here is what's referred to as Graham's law of effusion or diffusion. It applies to both of them. So when we're comparing two gases, this is all we need. Now before I get into some example problems with this, as we see here, this equation is written in terms of the rate for one gas divided by the rate for another, which is sometimes how the problems will be framed. But there's two other ways we can frame the questions as well, so we're going to be familiar with some of these variations. So one way we could frame these, especially if we're talking about diffusion, would be in terms of distance travel. So we should recognize that what we're comparing in that standard form of the equation are speeds or rates, which are given by distance divided by time at a very simple level. And so if we're framing the question in terms of how far do the gases travel, so in other words, if I want to have two gases race against each other, if I release samples of gases here and here at the front of the room, and over some period of time I measure how far they travel, how far they diffuse, we can also talk about then the ratio of those distances as well. Now because speed and distance are directly related, the distance that they travel is directly proportional to how fast they're going. So that, I think, makes sense. So it's the gas that's moving faster is going to move farther over a given period of time. And so what that means then is that the Graham's law equation is identical in terms of distance. The distance that one gas travels, A, over the distance that another gas, B, travels in the same period of time are just given by the inverse square root of their molar mass ratios. So this form of the equation, if we're talking about how far does something move in a given period of time, how far does a sample of gas diffuse over a period of time, it's the exact same equation as we saw before when we're talking about distances as opposed to rates or speeds. All right, but then there's another variation of this in terms of time. So if we're conducting the race between two gas molecules to see which one gets to the back of the room faster, let's say we release them up here and we see exactly how long it takes them to strike that back wall there. We can time that. And so if we're talking about a ratio of times that it takes for two gases to effuse or diffuse, speed, as we should recognize, is inversely related to time. So in other words, the gas that's moving faster is going to effuse or diffuse in a shorter period of time than the gas that's moving slower. Or if you think about it as a leak rate, if we have two gases leaking from a container, the one that's moving slower is going to leak out slower, and the one that's is going to leak out in a longer time. The one that's moving faster is going to leak out in a smaller time. So the speed they're moving and the time that it takes them to either leak or diffuse is going to be inversely related. So if we write this equation in terms of the ratio of the times that it takes two gases to effuse or diffuse, in this case it's going to be directly related to the square root of the molar mass ratios. Alright, so we do have to be a little bit familiar with this variation, where if we're talking about the time that it takes a gas to leak out of a container or to travel through space, we have to do the direct ratio A over B, as opposed to inverting the ratio like we do for speed or distance. All right, so don't let that trip you up. Think about it a little bit conceptually when you're doing these problems. The math is not too difficult here, so we can know that if we're comparing two gases, the heavier gas is going to move slower. The heavier gas is then going to diffuse slower. It's going to have diffuse less distance in the same time, and it's going to take longer to go a certain distance than the other gas. So always think about things in terms of those basic concepts to make sure that the answers that you get are reasonable, and we'll see how that works then in a few example problems. Alright, so let's do one example here. We're going to have an equal molar sample of hydrogen and helium. So hydrogen has a molar mass of 2.02, Helium, as we saw, has an atomic mass of 4 grams per mole. And we want to know which one diffuses faster and by how much. So here we're just comparing the rates of effusion, looking at the ratio of those two, which comes directly from the equation. So we didn't specify what order to write it in, but let's see what happens if we see what's the rate of the diffusion, or sorry, diffusion in this case, of hydrogen divided by the rate for helium. We can write it in either way, of course, but we're comparing two rates, so we're going to look at just the ratio of those two. And as we said, the equation that relates those is just the inverse square of the molar mass ratios. So molar mass of helium over hydrogen. So if we're comparing rate of hydrogen over rate of helium, on the other side of the equation it's going to be molar mass of helium over the molar mass of hydrogen, all under the square root sign. And now we just have to plug in the masses, the molar masses, and in this case they can be in the standard grams per mole unit because it's a ratio of 2, we don't have any constants in there, and so whatever mass unit we choose, which grams per mole is the one you always want to choose, we can just use that directly. We don't have to convert to kilograms like we did last time. Alright, so if we have a molar mass of helium on the top, that's 4 grams per mole. Molar mass of hydrogen on the bottom is 2.02 grams per mole. And when we take the square root of that number, which is 1.98, we get 1.41. And so what this means is the ratio of the rate of hydrogen divided by the rate for helium is 1.41. Another way of interpreting that is that H2 effuses 1.41 times faster. Okay? And that should hopefully make sense because the hydrogen is a lighter gas, which means it's moving faster, which means it should diffuse faster. So always think about it in those terms. Alright, so that's just a pretty straightforward application of Graham's law. And as it shows here, when we use this form of the equation, we're not going to get absolute rates of effusion or diffusion. We're going to get a ratio of two rates, and we're going to use that in some way. Alright, so any questions on this one? Yeah. Yeah, you're always comparing two gases. So these molar masses are the two gases you're comparing, and whether this fraction comes out to be greater than or equal to 1, or sorry, greater than or less than 1 will tell you which one's faster than the other. So this number is greater than 1, rate of hydrogen's on the top here, which means that the rate of hydrogen must be bigger than the rate of helium, must be moving faster. Okay? Does that answer your question? The conclusion wouldn't change. You would get basically 1 over this number, which is like 0.7, and that would tell you then that helium is slower than hydrogen because the ratio came out to less than 1. And so you would get the same conclusion either way. Now typically we're a little bit more specific in how we ask the question so that that kind of confusion doesn't come up. But really, whichever way you do it, you'll come to the same answer, you'll come to the same conclusion. And the same is true in other problems we're going to do here in a minute, where you can write these equations either way. Just keep in mind that if you flip one side of the equation, you'd have to flip the other. So if you started with rate of helium divided by rate of H2, that's perfectly fine, but then you have to make sure you do the same to the other side of the equation and flip that also. And no matter how you set this up, algebraically you'll end up with the same answer. Sometimes the algebra is trickier than others depending on how you choose to set it up, but it'll all work out in the end. You'll get the same conclusion or the same response that you need for this, no matter how you set it up. So there's no rhyme or reason as to which gas you put on top or on the bottom. You choose whatever you think you want to do, and you just set up the problem and go from there. Now, when I do them in class, since I have the benefit of foresight of knowing what the problem is and what the answer is, I typically set it up in the most straightforward way algebraically. But if you had done it the other way, you could still work out to the solution just with slightly more complicated algebra than what I'll show. Alright, so this one I think gives us a little bit more of an idea of a typical use for these problems, or a more specific way that we'll set it up. So let's say we have this situation here. It takes 1.25 minutes for 0.01 moles of helium to effuse. How long would it take for the same amount of ethane to effuse? Okay, so again, effusion is talking about leak rates. So if we time that it takes 1.25 minutes for 0.01 moles to leak out, how long would it take for the same amount of ethane to leak out 0.01 moles also. So in this case, we're talking about the ratio of 2 times. And remember that we said that speed is inversely related to time. The gas that's moving faster is going to leak out in a shorter time. The gas that's moving slower is going to take a longer time to leak out. So those two are inversely related, which means when we write the equation, whether we put C2H6 or hydrogen on the top, I'll put C2H6 on the top. Sorry, C2H6 or helium on the top. And then when we're talking about times, the relationship is going to be direct. So it's going to be the molar mass of C2H6 divided by the molar mass of helium. If we were talking about rates of effusion, or if we were talking about the distance that a certain gas travels in a period of time, we'd have to invert one side of these equations. Again, we can write it in either way. We could have put helium on top over here, C2H6 on the bottom over here, but then we'd also have to switch these two to keep the equality the same. All right, so there's, again, 2 different forms of this equation, depending on whether we're talking about time or rate or distance. There's a couple different ways we can do this. So what we're looking for here is the amount of time that it takes C2H6 to diffuse. So we're going to solve for that. So we're just going to move over, we're just going to cross multiply and move over the other term for the time that it takes for helium. So we can just solve for that algebraically, and then we just plug in the numbers. So the molar mass for ethane goes on top, that's 30.08. The molar mass for helium, which is 4, goes on the bottom. And then the time that it took helium to diffuse, we saw was 1.25 minutes. So we're going to multiply that ratio times 1.25 to find out what the time it takes for the other gas to effuse. And that comes out to 3.43 minutes. All right? And it's always helpful to make sure your answer makes sense, because it is easy to invert one side of these equations when you're using them. And we know that ethane, C2H6, is significantly heavier than helium. So helium is going to be moving faster, it's going to leak out faster, or take a shorter amount of time to leak out. So this one has a slower leak rate and then would take longer. And 3.43 minutes is clearly longer than 1.25 minutes, so at least our answer makes sense. We can always check that before we select the answer or type it into Blackboard. All right, so any questions on that? Same concept here, but here we're actually giving you one of the effusion times and then asking you to solve for the other one, so you have a little more information in this one to work with. All right, so questions? Back, someone?
How come you didn't put them in
Because here we're talking about a ratio of times. So the standard form of the equation, going way back to where I showed it, the standard form of the equation is in terms of rates, either rates of effusion or rates of diffusion. In that case, you do flip the two. So rate of A over rate of B is equal to molecular weight of B over molecular weight of A, all in the square root. That's what happens when you're talking about rate. But here we're talking about the amount of time that it takes to effuse. And because speed or rate is inversely related to time, in other words, the gas that's moving faster is going to have a shorter time, the gas that's moving slower is going to have a longer time. Because those two are inversely related to each other, we have to flip one side of the equation. In this case, they then become directly related to each other. The amount of time is going to be directly related to the square root of the molecular weight as opposed to inversely related. So there's 2 different ways, again, that these problems can be set up, and we just don't want that to cause any problems. And if you think about it logically or conceptually, I think that can help you decide which form of the equation to use, and also help you decide whether your answer is reasonable or not. Okay, any other clarification on this? Okay. And then I think we have one more to do. Yeah, so this is just another variation of the same theme. So if we have 7.23 milliliters of an unknown gas effuses in the same amount of time as 13.8 milliliters of argon under the same conditions, what is the molar mass of the unknown gas? All right, so here again we're using the the Graham's Law equation, and this time we're going to use it in the standard form, because if we're talking about a given period of time, if the gas that's effusing faster is going to have more of it leak out than the gas that's effusing slower. And so the rate for argon divided by the rate for our unknown x is equal to the inverse of the square root of the molar mass of x divided by the molar mass of argon. Alright, so here again we're not talking about the amount of time that it takes to effuse, we're talking about how much gas effuses in a period of time, which is directly related to then how fast those gases are effusing. So we use the standard form of the equation. And again, if we have two things under the square root, we can simplify this a little bit, at least algebraically, and recognize that this is a ratio of two square roots, in case that wasn't mathematically obvious. And then we're going to solve for the molar mass of x. That's going to be our unknown. And so we can just start putting numbers in. I think that's helpful to do instead of doing too much crazy algebra. So what we have here is the ratio of the rates in the same period of time. 13.8 milliliters of argon diffuses. So the ratio of the rates is going to be the ratio of the amounts of gas that diffuse over those period of times. So 13.8 divided by 7.23 is the rate of the two divided by each other. That's equal to the square root of the molar mass of our unknown divided by the square root of the molar mass of argon. And we said the molar mass for argon is 39.95 given to us here. And then so when we do some algebra, what we get is that the square root of the molar mass of x is equal to 13.8 divided by 7.23 times the square root of 39.95. And then if we want to find the molar mass of x, we just have to square both sides. So to get rid, we haven't done a lot of algebra with square roots yet, so in case you're rusty on that, if we have a square root on one side of our equation, we get rid of it by taking the square of both sides. So we square both sides of the equation. The molar mass of x becomes 13.8 over 7.23 squared times 39.95. And that works out then to 146 grams per mole. Alright, so again, the algebra here is not too bad, but it does involve square roots, which we haven't dealt with before. Always check your answer to make sure it's reasonable. This gas we know is effusing slower than argon because less of it leaks out over the same period of time. If it's leaking out slower, that must mean it's moving slower, which must mean it's heavier than argon. Argon has a mass of 39.95. Our unknown should have something larger than that, and that's what we got here, so at least it's reasonable. Alright, so any questions on that application? So really same equation, just solving for a different unknown, so that can be something we could ask you to do as well. So anything you want me to clarify on that? Okay. Now the last application of Graham's Law we're going to talk about is this type of experiment here, which I think you guys do in lab. Is that still true? Or have you done it yet? Yes, okay. Again, my knowledge of what happens in lab is poor, so I need you guys to remind me. Alright, so it's this type of experiment, which is a common diffusion experiment to sort of validate Graham's Law or use it to make some predictions. And so what you do in this experiment, things are kind of written small here, so I'll blow them up a little bit. You're doing a reaction between two gas phase reactants, and the one that you commonly do is ammonia gas, and then you react that with gas phase HCl. So typically the gaseous reactants, they diffuse out of an aqueous solution of those. So the two gases are going to react with each other to make ammonium chloride. It's an acid-base reaction, and that's going to be a solid then, because it's an ionic compound, and we know all ionic compounds are typically solid. So what you do here is you release one of your reactants at one end, typically by putting an aqueous solution of that at one end, and then you're going to put the other reactant on the other end, and those two are going to diffuse towards each other, and they're going to meet somewhere in the middle, and then you're going to form your solid here at the interface where those two meet. And again, because it's a solid, you can sort of see a little ring or a little line where those two form. Now, I've never done this experiment myself. I heard that it rarely works out as planned, which may or may not be true depending on your experience with it. But anyway, we can at least do some calculations and problems associated with it that hopefully will help you in the lab, and might come up a little bit on our homework assignments and tests as well. So the idea here is that we want to let the two gases diffuse through this tube, and they meet somewhere in the middle and they react with each other, and we can measure where that happens. So let's just write out what's going on here. We start at opposite ends of a glass tube. The two gases diffuse towards each other. Until they meet in the middle somewhere. And as soon as they meet each other, they're going to react and they're going to form solid ammonium chloride. Alright, so the two gases don't actually react with each other until they come in contact. And they don't come in contact until they both diffused far enough in opposite directions to meet each other. And what we can do is we can use Graham's law of diffusion, what we've been talking about now, to predict exactly where in our glass tube those two should come together and meet. Or alternatively, we can measure that for an unknown gas if we know that it's going to react, which if it's unknown, you have to know what it is to know it's going to react, so that wouldn't really happen. But we could still use this to at least validate Graham's law and make some predictions and things like that. So let's look at how the math works out. So let's say we take HCl and ammonia and release them from opposite ends of a tube, and the tube is 30 centimeters long, which is approximately the size of a 12-inch ruler. And we want to know how far does the ammonia travel before reacting with the HCl. So again, we're asking here which point in the tube do they meet each other and react with each other. So a simplified diagram of what's going on is you have a tube that's 30 centimeters long. We're releasing ammonia at one end, HCl on the other. This is going to diffuse some distance. This is going to diffuse some distance in the opposite direction, and we're going to measure the point where they meet and react with each other. And it's this distance here that we're interested in solving for. How far does the NH3 travel along this direction of the tube, as I've drawn it from left to right, before it meets with the HCl and before the two react with each other? So this is what we're interested in here, is this distance. So the first thing we can do is use Graham's law to set up a relationship between the two distances. So as we said, the distance that two gases travel under the same conditions, the distance that HCl travels divided by the distance that ammonia travels, or we can write it in the opposite way as well, it'll work out either way. This ratio of the distances is equal to the inverse of the ratios of their molar masses, all square rooted. Right, because again, the gas that's moving faster is going to move farther in the same period of time. So they're going to be using the standard form of the equation, and they're inversely related to the molar mass. And so we can just plug in the numbers that we have for these two reactants. The molar mass of ammonia is 17.03. The molar mass for HCl is 36.46. So that ratio and then the square root of those gives us the ratio of the distances. Alright, and so what that means then is that the distance that HCl travels is equal to 0.683 times the distance that ammonia travels. Alright, but again, this doesn't give us absolute values of any distance. It just gives us a relationship between the two from this Graham's law. So if we want to actually solve for what the distance is that ammonia travels, we need another equation to relate the two. Now we know that our tube is 30 centimeters long, so the gases are going to travel a total of 30 centimeters before they meet each other. In other words, the distance that HCl travels plus the distance that ammonia travels has to equal 30 centimeters. And what we're doing is we're solving for the distance of that NH3 travels, so we're going to replace the distance that HCl travels with 0.683 times that. So we're going to make a substitution here and say that 0.683 times 0.683 times the distance that ammonia travels plus the distance that ammonia travels equals 30 centimeters. Alright, so just a system of equations. We make a substitution to replace one of the variables, and now we can solve and find that the distance that ammonia travels is 17.8 centimeters. And presumably what you would do in the lab is you would measure that distance and compare it to the theoretical value and find, hopefully, that they're close to each other. Likely that they're not. And so that's what we see. We should, again, check our answer to make sure it's reasonable. Ammonia is lighter than HCl, so it's going to move faster, which means it's going to travel farther in the same period of time, which means that this distance should be something more than half of the 30 centimeters. So it's greater than half, so that at least makes sense, and we see that we calculated to be 17.8, which means that HCl would travel about 12.2 centimeters before they meet each other, a smaller distance. All right, so any questions on that problem, which, again, is, I think, directly relevant to things you did in the lab? Okay, so it's just a series of two equations. We use Graham's law to find the ratio of the two, and then the sum of the two is the total distance we can plug into there to get the final answer. All right, anything else on this topic before I move on? All right, so the last thing we're going to talk about in Chapter 8, I guess we're in, is real gases. So we've talked about ideal gases up until now, and ideal gases are one that they obey the ideal gas equation, which we all know is PV equals nRT. And then they also follow all of those postulates of the kinetic molecular theory of gas. They're gases that have no volume, they're gases that don't interact with each other, they're moving around randomly and all that stuff, all those four postulates we started with today. So if we have an ideal gas that obeys the ideal gas equation, the ratio of pressure times volume divided by nRT, so if we just divide both sides by nRT, that should be equal to 1 for an ideal gas. So for an ideal gas, if we were to take the ratio of pressure times volume divided by nRT, at any given pressure it should be exactly equal to 1. That's what this red line is showing here. So an ideal gas, that ratio will always be 1 if it obeys the ideal gas equation. But the reality is that all gases deviate from this somewhat. So they deviate in some different ways, which is related to the molecular nature of the gases and some other things about them that we'll probably get into more in the next chapter. But if we have a sample of hydrogen, its plot would actually look like this. So as we go to higher and higher pressures for hydrogen, we're going to get some positive deviations from the ideal gas law. Now in reality, to see significant deviations, you have to go to really, really high pressures. So the pressures that we operate on in our daily lives, the ideal gas law is still largely obeyed, but over high pressures we get some deviations. Now other gases are going to have some different behavior associated with them. So if we look at nitrogen, it's going to initially dip down and then it's going to go up. So nitrogen has sort of a different behavior. Initially we get negative deviations from the ideal gas law, but then at high pressures again it deviates in a positive fashion. And then different gases are going to have slightly different profiles. So again, I'm drawing these all qualitatively, and we're not going to hold you responsible for memorizing these differences, but the point is that different gases have different deviations from the ideal gas law. So again, they all should ideally follow a straight line of 1 at all pressures, but in reality the ratio of PV divided by nRT is not going to be equal to 1, especially when we go to really high pressures. And then the last one I'll show is if we go to CO2, it has even larger deviations. And what this, I think, shows you qualitatively at least is that the magnitude of the deviation from the ideal gas behavior is somewhat related to the molar mass, and that will make more sense in things we talk about in the next chapter. So the heavier gases tend to have more deviations or larger deviations from the ideal gas behavior. A light gas like hydrogen would follow the ideal gas law relatively well over a wide range of pressures. So this is the reality of the situation. No gas behaves ideally, and this is especially true as we go to really high pressures. So let's talk then about under which conditions do real gases behave most like ideal gases. So there is no gas that is actually an ideal gas. That's always just an approximation. But under certain conditions, any gas will behave in a relatively ideal fashion. And so the two conditions where they behave most ideal are going to be at low pressure. And so the chief reason why the gases deviate from ideal behavior is because the one assumption about the kinetic molecular theory was that the gas molecules aren't interacting with each other at all. And that part is actually false. Thank you. All right, so that part of the ideal gas, the kinetic molecular theory is actually false. They do interact with each other. And so, but if we go to low pressure, the gas particles are very far apart from each other, and so they don't interact very much. So in the limit of low pressure, as the pressure approaches zero, the gas will behave ideally. So when the gas molecules are very far apart, that minimizes their interactions and then minimizes the deviations from the ideal gas equation. Or in other words, the volume of the particles, which is non-zero in real life, is still much, much smaller than the volume of the container that the gas is in. And so you don't have to worry about, so you don't have as big of deviations from that ideal gas behavior. So again, the kinetic molecular theory assumed that the volume of the particles was zero. That's not actually true. That's responsible for some of these deviations. But if you have a really low pressure sample of a gas where the molecules are really far apart from each other and occupying a large volume, in those situations you would have smaller deviations. And then the other situation when the deviations are smaller at higher temperatures. So if we increase the temperature of a sample of a gas, the particles are moving much faster, as we just said, we just introduced today. So if the gas molecules are moving very fast, they're going to spend very little time interacting with each other. Because again, it's these interactions of gas molecules with each other that's another source of deviation from ideal gas behavior. And if the gas molecules are moving really fast, they're not going to interact with each other for as long. They're going to just zoom right past each other, and they're not going to see each other as much. So if we want a gas to behave ideally, if we want it to follow the ideal gas equation as closely as it can, we go to very low pressures and we go to very high temperatures. Yeah, I stop every time you're talking if you haven't noticed yet. Okay? All right, so then when we talk about real gases, we have an equation that dictates their behavior. So the ideal gas equation, as I said, doesn't work perfectly, so we have some corrections that we can apply to the ideal gas equation to get what's called the van der Waals equation. We're not going to do any calculations with this, but we just want to understand it conceptually and know what these corrections refer to. So starting with PV equals nRT, we can make some corrections to pressure and volume to make the gases fit a little bit better to this modified equation. So pressure times n squared A over V squared times volume minus n times B is equal to nRT. So PV, N, and T still have the same definitions, but then we have these other parameters A and B that adjust the ideal gas equation and allow it to then work better for real gases. So this small letter A here, which is a correction that's applied to the pressure here, this adjusts for interparticle interactions. So this adjusts for the fact that the gas particles are actually interacting with each other. And it adjusts the pressure, makes the pressure slightly larger than what we actually measure. And this is because, especially at relatively low pressures, where we start to see these deviations when we're not going to too high pressures, the deviations, you basically have some slight attractive interactions between the gas molecules, some what we call intermolecular forces that we'll deal with in Chapter 9. And so because of that, because the gas molecules are attracting to each other a little bit, they're not hitting the walls of the container as forcefully or as often as they normally would. And so you have to adjust, you have to apply an upward correction to the pressure to make it a more ideal value. Okay? So that accounts for the fact that the gas molecules have some interactions with each other. And then this other term here, B, with the other van der Waals parameter, adjusts the volume. It's adjusted to account for the volume of the particles themselves. All right, because as we said, the ideal gas equation assumes that the particle volume is zero. In reality, that's not true. And so we can adjust that by a factor B, also multiplied by the number of moles of gas that we have. That accounts for that's basically the molar volume of the gas. All right, so that accounts for the volume of the gas particles. And so these A and B terms here, which are the van der Waals parameters, these are empirically determined parameters. So they're not something that we can calculate or that we have to really worry about memorizing. So these are called van der Waals parameters. They're experimentally determined, so they're not calculated, or there's no real first principle way to get them. And they're unique for each gas. So when we're applying corrections to the ideal gas equation using the van der Waals equation, we're using different values of A and B depending on what gas we're talking about. So again, we're not going to use this equation to do any calculations on our homework or test problems, but we want to understand that the ideal gas equation doesn't work perfectly for real gases. We want to understand the reasons for those deviations and that we're able to then apply some corrections to account for those. So we don't want to know, so that's as details we're going to go into with real gases. You'll see some conceptual questions on the homework that'll help you get used to the types of things we'll ask. Now, what I'm going to move into today is a little bit of a transition into Chapter 9, but before I do that, yep.
So that B squared on the numerator, is that velocity or volume?
Everything's still volume. So it's capital V, so we're just correcting these, and they're both a function of the number of moles of gas you have and the volume of the container. But yeah, it's all just pressure, volume, number of moles, and temperature as we would have for the ideal gas equation. Now, to transition into Chapter 9, which I'm going to cover in the virtual lecture that I'm doing on Wednesday, let's get a couple of key concepts out of the way. I actually repeat these in the video that are on Wednesday, so there's a little bit of overlap, but just to get us oriented a little bit about what we're going to talk about next. So when we move into Chapter 9, which is where we're going now, we're going to transition into that now. We're going to now talk about what are called condensed phases. So we're moving on from gases, we're going to talk about liquids and solids. And we want to know some of the key differences between gases and condensed phases. So the key assumption from the kinetic molecular theory, the one that we just learned today, is that gas particles have no interactions with each other. Alright, so there's no interactions between gas particles. They're neither attracting nor repelling each other. But the reality of the situation is that when we talk about real gases, or we talk about liquids and solids, the condensed phases that we're going to deal with in this chapter, all of the atoms and molecules are in constant contact with each other, especially true in condensed phases. So in these condensed phases, atoms and molecules are in constant contact, which means they are interacting with each other. And these interacting forces is what holds them together in their condensed phases. So in liquids and solids, we know that they don't just spontaneously vaporize and become gases, at least under any normal period of time. They don't do that. And the reason for this, and the reason that the molecules don't just fly apart from each other and become gases, is because there are these types of forces that are holding them together in the solid or liquid phase. And a lot of what Chapter 9 deals with, especially at the beginning, is defining the types of forces that hold atoms and molecules together in these condensed phases. So what we're going to talk about then are what are called intermolecular forces in this chapter. And again, we're going to define these more precisely a little bit later on, which we'll cover on Wednesday. But what is an intermolecular force? So the Latin root inter means between. So an intermolecular force is a force of attraction between two atoms or molecules, two separate atoms or molecules. Let me write that a little bit more precisely. Separate molecules or separate atoms. Alright, and so a common source of confusion in this chapter is that when we're talking about intermolecular forces, we're not talking about bonds that hold atoms together in molecules. Alright, so when we talk about intermolecular forces, we're not talking about chemical bonds. We're talking about the much weaker forces that are responsible for keeping two separate atoms or two separate molecules together in a condensed phase. So intermolecular forces have nothing to do with bonds, and when we're comparing the strengths of intermolecular forces, if we want to ask, which substance has a stronger intermolecular force, substance A or substance B, it has nothing to do with covalent bond strengths. Okay, so there's always this little source of confusion that comes up about the difference between bonds and intermolecular forces, and they're really two separate topics, okay? They depend on two separate things, two separate parameters. And so when we talk about covalent bonds, which we talked a lot about back in Chapter 3 in this course, covalent bonds or any other type of bonding interaction are what are called intramolecular forces. So intra versus inter, obviously they look the same, but they mean very different things. And so when we're talking about these intermolecular forces, we're not talking about the bonds that hold molecules together. We're talking about weaker forces that hold two molecules in contact with each other. All right, so they're two separate topics, and they depend on two separate things, as we'll get into in more detail. And then the last thing that I want to prime you on before we get into the details of Chapter 9 next time are phase changes. So Chapter 9 is going to talk about the different phases of matter besides gases, liquids, and solids in particular. And so we're also going to deal with then changing the phase between two of these. So if we talk about the phase change from a liquid to a gas, as we likely all know from our everyday life, when you change a liquid to a gas, that's referred to as boiling. And then when we go the opposite direction, if a gas changes into a liquid, we call that condensation. So those are the phase changes associated with interconverting a liquid in a gas. And the boiling point, we're going to give a more precise definition for this later on, much later on in this chapter, but the boiling point, for now, we can think of it as the temperature at which a liquid and a gas interconvert. All right, so that's the boiling point. And the reason that this is important to get out of the way first is this should be a review for most of us, but when we talk about intermolecular forces, the forces that hold atoms and molecules together in condensed phases, the strength of those intermolecular forces is going to then relate to the boiling point. So that's why we're talking about this now. And then the other phase change we're talking about is between liquid and solid. If we go from a liquid to a solid, that's referred to as freezing. Now we know that water freezes at 0 degrees Celsius, which doesn't happen very often in Houston, at least outside. But that's the process of freezing, as we know, going from liquid to solid. The opposite process is called melting. And the temperature at which those occur is referred to as the freezing or melting point. Those two are used interchangeably, but they're the same temperature for a given substance. So again, the non-precise definition of this is that the freezing or melting point is the temperature at which the liquid and the solid interconvert with each other. All right, and as I hinted to earlier, the reason that this is important is because a lot of what we're going to do at the beginning of this chapter is talk about different types of intermolecular forces and how to compare them between two different substances. And if you have stronger intermolecular forces, which we'll abbreviate as IMFs, that's going to correlate with a higher boiling point and a higher melting point. So if the atoms and molecules are held together more strongly by these intermolecular forces, you have to go to a higher temperature to break them up into a less condensed phase. So that kind of sets the stage for what we're going to talk about in Chapter 9. And as I said, the first lecture for that will just be online because I won't be here. So if I don't see you tomorrow, I will see you sometime next week.